we are going to discuss about the Doppler effect. Usually, the Doppler effect is happening in the sound wave, electromagnetic waves, and then other kind of waves. But particularly, we are going to look at in sound wave what is the Doppler effect. Already, we know what is the sound wave because the waves are longitudinal wave. The sound waves are vibration. The wave vibration it will be parallel to the propagation. That's why it is called the longitudinal wave. But in the sound wave, what is the Doppler effect? And Doppler effect means the short definition for the Doppler effect. There is a change in frequency. There is change in observed frequency. When the observer or the source or both of them are in motion. So this is known as Doppler effect. So that means the observed frequency, it will be different from the original frequency because the source will produce a frequency 70 kilohertz or 80 kilohertz, but the observed frequency may not be the same. The observer is in motion, the observed frequency may be lower or higher. So the frequency will be different from the 70 Hz. That is called the Doppler effect. But either the source will move or observer will move or both of them are in dynamics. But if observer as well as the source, both of them are raised, we can't observe this Doppler effect. So there is no Doppler effect at all. For those cases, both the observer as well as the source, both of them are at rest. So there are three cases we can observe this Doppler effect. The first case, observer at rest and source is in motion. That means, suppose observer may stand here at the point O. The sound wave, maybe you can consider the speaker producing the sound wave. The speaker is either moving away from the observer or towards the observer. So in these cases, we can observe that there is a change in frequency compared to the original frequency. The second case, we can observe the Doppler effect. Now the source, we can keep it at rest. At a point O, we can keep the source of the sound wave at rest. The observer in motion towards the source or away from the source. So this is a second case. Here we can write it as the observer in motion and source is at rest. The third case, we can observe the Doppler effect. Both of them are in motions, like the source and the observer are in motion. That means the observer may stand here, the source will be here. They are moving in any of the directions. So in these three such cases, we can observe the Doppler effect. First, let's discuss the first case. The observer is the case 1. The observer at rest and source is in motion. So that means the source is moving away from the observer. We can keep the observer in the stationary frame. That means the frame itself is at rest. We can picturize this problem first. So keep the observer position as O. The observer is standing here. In this, maybe we can now we are assuming that the one-dimensional problem. So that means along the only one direction, the source is at S1 position. This is a source position. This is the observer position at that starting time. The length between observer as well as the source, it's a OS1 equal to, we can call it the L. So at time t equal to t1, the source emit the first crest. So we assume that at time t1, the source emit first crest. So that means what is the time taken to reach the observer, the first crest? Maybe the source is now emitting the first crest. So it will take some time to reach the observer. What is the time taken? Maybe now we are assuming the wave velocity. The wave velocity, the sound wave velocity will be v. So what is the time taken means the time taken to reach the observer for the first crest, the t1 it will be equal to, already we know the velocity definition. Velocity is nothing but the distance traveled by the time taken, or time taken equal to the distance traveled, the L distance it needs to travel the first crest divided by the velocity of the sound wave. This is that at time t1, it will take the first crest, it will take the time L by V time to reach the observer, because now the observer is at rest. Okay, after the first crest, let us assume the source is moving along this direction. This direction with a velocity Vs, because S represents the source velocity Vs. So now the new position of the source will be S, we are assuming. During this movement, what is the time taken for this movement means we are assuming it's the period of the sound wave. That means first it is emitting the first crest. Now the second crest. So at the S2, it start to emit, the source start to emit the second crest. The duration, the time, it will be equal to the t0. The crest to crest, the time taken, the produced one crest to another crest, the duration will be the period of the wave. So now if you are asking the question, what is the distance traveled by the source, the velocity Vs means, already we know distance traveled is nothing but velocity times time. Here the velocity is nothing but the source velocity. The time taken is nothing but the period of the wave. During this distance travel, it emits the next crest. That means it producing the period of the wave. So now we can ask question, what is the time taken for the second crest? Because the second crest it is producing here at this S2. What is this crest to reach the observer at O1 means the second crest take time t2 T2 to reach the observer. That time T2 is nothing but the period of the wave, because it's a second crest. It need to produce the production for the second crest. It's the duration T0 plus the second crest. It need to travel the distance, this much distance, to reach the observer. So the distance is nothing but L plus Vs plus T0. So the distance traveled by that time taken, uh, the distance traveled by the velocity of the sound wave. So this is the net distance it need to travel. The second crest need to travel to reach the observer. That distance is nothing but L plus, maybe you can write it here, L plus Vs plus T0. This is the distance it need to travel. Thereby the velocity of the sound, it will tell us the time taken. Plus additionally, it will take the period of the wave. Similarly, we can find the T3, T4. Suppose if you are asking the question, what is T3? So that T3 means the time taken for the third crest to reach the observer. During this time, the period of the wave will be 2 T0, because the third crest means this is the first crest, this is the seventh crest, this is the third crest. So this duration, this is the production of the third crest. This is a duration 2 T0. This is T0. This is another T0. So 2 T0. This is the time it will take to produce a third crest. Then this crest need to travel to reach the observer. That time it will be the distance traveled. That means 2 Vs T0 whereby the velocity of the sound wave. Because second crest it is L plus Vs T0. The third crest it will be 2 Vs T0. Fourth crest it will be like 3 Vs plus T0. So like that it will go for the n plus 1 crest. That time, for the nth crest, the time taken will be, it's a T n plus 1. It should be equal to n times T0 plus L plus n Vs plus T0 divided by the V. So this is the n plus 1 crest, nth crest, the time taken for the nth crest. So first crest is T1, T2, T3. For the nth crest, the time taken it will be Tn plus 1. So this is time taken for the n plus 1th crest, nth crest time taken. This is for the this is for the time taken to reach n plus 1 crest to the observer. Okay, fine. Let's take this the observation by the observer. Now we can ask a question from the first crest to the nth crest, n plus 1th crest. Actually, here it will become n plus 1th crest. N plus 1th crest, because the first crest T1, second crest it is the time taken T2, third crest T3, nth crest Tn, n plus 1th crest, it's like Tn plus 1, but the period will be n T0. The distance moved by the source will be n times Vs T0. So that is here I have mentioned the period for the n plus 1 crest it will be n T0. The distance moved by the source will be n Vs plus T0. Now we can ask the question, during this time interval like t1 to tn plus 1, there will be n number of that time period. We can ask one question, what is the time period? What is the period of the wave? Period of the wave. So the period of the wave, it's nothing but t naught. It will be equal to the difference between the n plus 1 plus minus first crest divided by the number of period. So this will tell us the period of the wave. Already we know that Tn plus 1, it is equal to n t naught plus L plus n Vs t naught divided by V minus the T1, it will be, it's nothing but L by V all divided by the n. So we can like cancel the L by V naught, L by V naught here. If you are cancelling these two, then we will get n t naught plus n Vs t naught by V whole divided by the n. We can take the t naught n outside, n t naught outside, inside 1 plus Vs by V whole divided by n. So we can cancel 1n and 1n. Then here actually what is the period of the wave observed by the observer? Because the period is not same. The period for the source, it will be t naught. The period of the wave at the source, it's a t naught. But the measured period by the observer, it will be not same because the source is moving away from the observer. So we should not take t naught. Here we are taking the t, the period of the wave observed by the observer, observed by the observer, it will be t. The t is nothing but the difference between the n plus 1 plus 2 first crest divided by the number of period. So this will tells us the period observed by the observer. So now the period, it will be equal to, it's a t naught 1 plus Vs by V. This is a period observed by the observer. It will be in general the large because the velocity of the source, it will be small compared to the velocity of the sound. Here Vs is the source velocity, V is velocity of the sound. Anyway, this ratio, it will be less than 1. Still the summation inside the bracket will be greater than 1. So the original period of the wave at the rest frame, it will be t naught, but the observed period, it will be larger than the original period when the source is moving away from the observer. Now we can ask the question, what is the measured frequency? Because we gave the definition for the Doppler effect in terms of frequency. So what is the observed frequency? Already we know the frequency equal to 1 by the period. If you are taking this definition, the observed frequency, the f equal to, or nu, some text maybe represents it's a nu. So nu equal to 1 by t. So already we have the derivation for the t. It's a t naught 1 plus Vs by V, or the 1 by t naught we can call it is equal to the original frequency of the sound wave in rest frame. So the observed frequency equal to the original frequency time. You need to push this 1 plus Vs by V to the numerator. It will be inverse. Suppose it's using the binomial expression, we can expand this inverse, but let us assume the source velocity is much less than the velocity of the sound. Maybe the velocity of the sound will be 330 meters per second. So the source velocity we can consider is much less than that. So in that case, we can approximate the binomial expansion up to second term. That means 1 minus Vs by V. So already we know the binomial expansion 1 plus nx equal to 1 plus x whole power n equal to 1 plus nx plus n into n minus 1 by 2 factorial x square. It will go like that. So we can approximate up to second term when this ratio will be much less than 1 Vs by V naught, because if the source velocity is less than the velocity of the sound, so we can assume the binomial expansion up to the second term. Here n, here it's minus 1. So the observed frequency is always less than the original frequency, because it's a 1 minus the ratio. It will give the less quantity. On the other hand, if you are assuming the source is moving towards the observer, that means the velocity now it's towards the observer. So the source velocity we need to replace by minus Vs. So if you are replacing with the minus Vs, now the observed frequency for the case source is moving towards the observer, the measured frequency by the observer equal to nu naught 1 plus Vs by V. Now the inside the bracket the quantity will be greater than 1. So the observed frequency is always higher than the original frequency of the source. So this is the case 1 when the source is in motion either away from the observer or towards the observer, but then now the observer is at rest. These are the two frequency region. We can measure the observed frequency according to the Doppler effect. In the case 2, now we are going to look at the Doppler effect in the observer is in motion and the source is at rest. So now we will picturize this problem. We can keep the source at S. Now the source is at rest. It emits the sound wave in all directions. The observer initially at a distance L from the source at a point O1. At time t equal to t1, the source is emitting the first crest. So the first crest to reach the observer at a time t1. So the time taken by the first crest to reach the observer at O1, because now the position of the observer is at O1, it will be equal to the time t1 equal to, again we are going to use the velocity definition, the distance traveled by the velocity of the sound wave. V represents the velocity of that sound wave. After a time period, let us assume that the observer is moving with a velocity V naught in the positive x direction. So the velocity of the observer is V, the small o. After the time period t naught, assume that the observer position is O2. During this time period, the source is emitting the second crest. That means the first crest, second crest, this is the first crest, this is the second crest. Now this wave is traveling, the duration between these two crests in the time domain it is t naught. That is the period of the wave, the original period of the wave. The distance traveled by the observer during this duration, it will be equal to the v naught times the t naught. Now the distance between the source and the observer, it will be the new distance, that will be equal to the original distance at a time t equal to t1 plus after the time period the distance traveled by the observer, it will be equal to v naught times the t naught. Now this is a new distance between the observer and source, that is the SO2. Now the time taken by the second crest to reach the observer at position O2. This will be equal to the time t2 equal to the period of the wave, because the time taken for the generation of the centering, that is period is t naught, plus the time taken by the second crest to reach the observer O2. That time is equal to the distance, the new distance traveled by the velocity of the sound wave. The new distance, it will be equal to L plus V naught plus T naught divided by the velocity of the sound wave. This is the duration the second crest will take to reach the observer. Similarly, we can derive the third crest to reach the observer. The time taken by the third crest equal to 2 t naught plus L 2 v naught t naught divided by the velocity of the sound wave. So the nth crest, it is generated, the n plus 1 crest to reach the observer, that will be equal to the n times t naught plus L n times v naught t naught divided by the velocity of the sound wave. Now we can ask one question: what is the period of the wave measured by the observer? That is our question. So we can write it here: the period of the wave measured by the observer equal to the period we can call as t, that should be equal to the time taken for the n plus 1 crest minus the time taken for the first crest divided by the total number of the waves, the numbers it's generated during this time period. The total number, the n number of wave generation happening during this time interval. If you are dividing these two, we will get the period, the measured period by the observer. So the t equal to t n plus 1 already we got derived, n t naught plus L plus n v naught t naught divided by the velocity whole divided by the n minus the t1, it will be equal to L by V. So we can cancel this L by V and L by V. The measured time period, it will be equal to, we can take the n t naught outside of the bracket, so it will be equal to 1 plus v naught by V whole divided by the n. We can cancel this and this one. The measured time period by the observer, that will be equal to t naught 1 plus v naught by V. So this is a period measured by the observer. Here t naught represents the original time period of the wave at the rest frame. V naught represents the velocity of the observer. V represents the velocity of the sound wave. But here v naught by V, it is less than 1. Anyway, we are assuming the velocity of the observer always less than the velocity of the sound waves. So for this case, 1 plus less than something 1, it will be the inside the bracket, the quantity, it will be greater than 1 times the t naught, it will be greater than 1.5. something greater than the period of the wave. That means the measured time period it will be greater than the original period of the wave when the observer is moving or receding away from the source. So the period will be elongated for the observer. Now we can measure the frequency. What is the frequency measured by the observer moving away from the source? The frequency measured by the observer moving away from the source. We have the relation, the measured frequency equal to 1 by the time period. So 1 by the time period is T0 plus 1 plus V0 by V. So 1 by T0 it will be equal to nu naught, the original frequency of the source at the initial rest frame. If you are pushing this bracket into the numerator, it will be inverse of the quantity. Again, we are going to make the binomial approximation when the velocity of the observer much less than the velocity of the sound wave. The ratio V0 by V is much less than 1. For this case, we can approximate the binomial expansion of the second term. That means the observed frequency equal to the frequency 1 minus, because we know the binomial expansion 1 plus nx whole power n equal to 1 plus nx plus n into n minus 1 divided by 2 factorial x square. It will go the series like that. But if the x is much less than 1, you can approximate this expansion up to 2 times. That will hold the result will be good. So if you are approximating up to the second term, it will be here n position that is minus 1. So minus V0 by V. This is a measured frequency by the observer. It is always less than the original frequency because inside the bracket the quantity is less than 1. 1 minus something decimal, so it will be less than 1. So measured frequency by the observer always less than the original frequency of the source. So in the case, suppose the observer moving towards the source. The velocity V0 you can replace by minus V0. That is the one thing we can do, or else we can very formally. Suppose if you are replacing this V0 by minus V0, the measured frequency by the observer equal to original frequency of the wave plus minus into minus plus V0 by V. Because the minus V0 represents now the velocity just opposite to the previous one or in negative x direction. So 1 plus V0 by V. Now if you look at this measured frequency, it will be always greater than the original frequency of the source. So this is the case 2 when the source is at rest, observer is in motion. The measured frequency is always less than the observed frequency when the observer is receding away from the source. When the observer is moving towards the source, the measured frequency by the observer is always higher than the source frequency. This is another case for Doppler effect.